This optimizing lifecycle costs for pumps and powertrains using FMI co-simulation. Let's start by breaking down this title a bit so we all are on the same page. So optimization in this case means that we want to find the lowest feasible cost for equipment in a process in the design phase. And lifecycle here essentially means the total cost of the equipment, including the upfront cost of the purchase and installation, but crucially also operational costs, such as electricity consumption. And powertrains in this context, also known as drivetrains, you may know it better with that term. In this context, it contains motor and frequency converters. So just an overview of the presentation, I'm going to introduce the background, why this is even something we want to do, which softwares we used, and the FMI implementations of the two. And then briefly simulation results, some technical difficulties, and what we're going to do in the future if we have time. And hopefully I can show the demo model simulation working if I have time for that at the end. So introduction. So these are some numbers that we found while searching for sources, but essentially 40% of world's electricity is currently consumed by electric motors in buildings and industrial applications. And approximately 75% of these industrial motors are used to run pumps, fans, and compressors. And this machine category specifically has high potential for major energy efficiency improvements. And it's estimated that there's roughly 300 million industrial electric motor frequency converter systems operational globally right now. And by choosing the optimal equipment size for all processes, there's a potential to reduce 10% of global electricity consumption. So the goals of our study was to essentially create this kind of co-simulated equipment selection, where we want to find the optimal size for equipment in a small demonstration process. And the tools we used for that was Apros Advanced Process Simulator and ABB's Virtual Drive. And what we call collaborative digital twin approach is essentially the approach that we wanted to investigate. And here, the collaborative part means that we have different subcontractors providing their equipment as FMU models during the design phase, which we can then use to find the optimal size of their equipment in the whole process by dynamic simulation. And our approach in this case was FMI co-simulation. So we implemented the master algorithm for Apros and the solver algorithm or slave algorithm for virtual drive. So the dynamic process simulator was Apros 6 specifically. It contained the model and was model and simulation of the process and automation, including the pumps. And the history of Apros goes back way back in time to 1970s and the commissioning of the Loviisa nuclear power plant in Finland. But in our use case, we didn't use any nuclear libraries. We just used the dynamic process simulator part of it. And Virtual Drive is ABB's standalone executable that contains math functions for motors and drives. And it's especially useful together with the drive size tool that ABB provides, that you can then create essentially virtual versions of physical ABB drive products. That's where the name comes from. They are virtual drives. And these virtual drives allow users to assess the behavior and check different sizes of drives in standalone mode or using a custom inter-process communication interface developed at ABB. And generally speaking, when people use Virtual Drive and configure it, they use a software called Drive Composer Pro to configure it and monitor it. And that's the primary kind of workflow of using it. And in our case, we implemented an FMU version of this virtual drive containing the motor and drive behavior. So the demo Apros model was very simple. It was just a proof of concept at this point. And you can see it schematically below. Essentially, what we do is we pump water to a tank. You can see the pump is this square with this triangle. So water is being pumped to a tank at the top here, and the outlet flow varies. So we need to control the liquid level of the tank with a control loop. So level control loop, this LIC box, keeps the liquid level within an allowed range, and the output of this level controller is the pump rotation speed, which is given to the drive plus motor component in this model, which is the virtual drive. So this INV in this picture is the virtual drive FMU model. And the virtual drive then returns the pump shaft torque, and Apros uses the pump shaft torque to determine the pump rotation speed. And from this, the pressure generated to the fluid is calculated together with pump curves. And the Apros model compared to the schematic view can be seen below. So all the same components in the same places can be seen. So we have the level control loop and the virtual drive FMU as components in this Apros model with the pump and water level and these valves controlling the outlet flow, and on the right, so changing the outlet flow. So implementing the FMI algorithm for Apros. So specific details is that Apros 6 is essentially it's a Java application built on top of semantics. It contains a solver written in Fortran, but due to its Eclipse-based product, this semantics-based product, we can extend it with plugins. So we can create Eclipse plugins for it. And that's what we did in this project. We created what we call Apros 6 FMI Importer plugin that contains FMI 1 and 2 co-simulation capabilities, and it's a prototype at this point. And the specific details how the plugin works can be seen here. So when the users want to import an FMU model to Apros, they are called user components. We essentially create a user component in Apros that they can then use in their model that is the FMU model under the hood. And whenever Apros, the solver, triggers pre-step actions, our user components actually subscribe to those and are configured to execute a custom script. And this script uses Java native interface. As you recall, Apros was a Java-based program, so it uses Java native interface to load this C implementation of FMI library to pass data between the Apros model and the FMU models. And the virtual drive's FMI implementation was a bit different. This is not unique in any way, but it was a bit different than the standard approach. So because Drive Composer Pro is so tightly used with virtual drive, we still wanted the users to be able to use that, because Drive people who are familiar with virtual drive, they want to use Drive Composer Pro when creating their drives. So we didn't want to take that away. But instead, we created a separate, what we call FMI wrapper, which is just essentially any old FMU model, but internally is a C program that communicates with this custom inter-process communication interface with virtual drives. So the benefits here is that we don't need to modify virtual drive essentially at all, but we create this new plug-and-play FMU model that is capable of communicating with existing virtual drives, reusing the interface that already exists for virtual drive. And the simulation results, the blue dotted line here in the middle, you may be able to see it starts at value 2. So that's the tank level set point that we wanted to keep the model at, the liquid level at. And we have some accepted values, so upper and lower limits are the other dotted lines, the yellow and gray dotted lines, starting at 3 and 1. So the pump, motor, and frequency converter were there wasn't any fancy algorithm choosing them. We chose them manually. So we chose specifically equipment that was underdimensioned. We chose specifically overdimensioned equipment, and we chose specifically optimal equipment to see that the co-simulation and the models actually reflect our kind of internal knowledge of the system. So that as a proof of concept of the dynamic model and the co-simulation approach. So from these simulation results, we can see that the underdimensioned equipment couldn't even reach the set point, it just flat refused to do it. It wasn't powerful enough. And the overdimensioned is keeping it very well. You can see it's the brown line. However, it's costly. It's too big. So even though it's fulfilling its task perfectly, it's costing too much. So what we wanted to check was, okay, a bit smaller one, is it still able to do it? And yes, it was. So the optimal choice is something that does the task at a lower cost, but within the limits. And some technical difficulties, we stumbled upon the fact that the custom interface, this interprocess communication for virtual drives, was much slower than the FMI interface itself. Of course, if you think about it, it's pretty obvious that FMI is very fast, and anything that uses some kind of process communication or other calls between programs is going to be smaller than that, slower than that. Sorry. So essentially, we try to keep, let's say, calls from this FMI wrapper to virtual drive as minimum as possible. So only ever in this FMI2 do step function will we actually do any interprocess communication calls to virtual drive, rather than doing it all the time. For example, with every set, we would directly set it to virtual drive. No, we use this do step as the synchronization point. And the first prototype that we built for this plugin for Apros, this FMI importer, it lacks parallelization, which of course means that if you have a large model with multiple FMUs, it's going to slow down very much. And there's also some overhead by using Java native interface wrapping. So there's room for optimization there as well. So every function calls needs to go through Java and C to the FME model and back. So there's room for improvement there. So in this simple demo model that you saw, if we set the step size to 0.1 seconds, which is large in many industrial cases, but actually very small for our model. Our model didn't need this small. So in that case, simulation speeds were roughly 3 times faster than real time. But as you can see in the video I will show next, the larger step sizes improve the speed. So in the video, it's actually 30 times faster than real time. And the next slide here, sorry. So future work is to actually use the same approach in a real customer case, with a real process being designed, and essentially get subcontractors to provide FMI models of their equipment and integrate it into a process plant simulation model. And after that, we can use system level optimization to find optimal equipment sizes for the whole process. So we can imagine there being dozens of these powertrains being optimized there. So there we hope that we can find ecological and economical equipment sizing solutions with this approach. Right, let's just quickly look at some numbers on the screen. You can't see the simulation time, it's so small here, but 30 times faster than real time simulating of this FMU model, which is the FMI wrapper, communicating with an external virtual drive, which has been configured with this completely different software, this Drive Composer Pro. And Drive Composer Pro also contains these monitoring capabilities of virtual drive. So all the data doesn't have to go through the FMI interface to be monitored. You can monitor it in this Drive Composer as well. Right, that's it for me. Thank you very much.